Thanks, Alon, and thank you everyone for being here. So this is going to be our tutorial on decision-theoretic forecasting. This tutorial was prepared in collaboration with Nika, Kunhe, and Eric. Nika sadly could not be here today, so I will give a brief introduction, and then Kunhe and Eric will take it away with the more technical part of the content. Now, we want to point out that, this can be a rather technical material, so we do have specific spots for pauses for questions throughout the tutorial. But if at any point in time you also have questions, feel free to chime in, and then we have time for questions at the end of each part as well. Okay, with that in mind, let me begin. So, why forecasting? So currently we have a wealth of data available and extremely powerful ML models. So there's no wonder that forecasting, identifying, predictions about events, forecasting has become ubiquitous in many aspects of life. And just to give you two very different examples of where forecasting can be employed or it can be useful, on the one hand, you may want to answer, if the weather app says that there's a 70% chance of rain, then how exactly should I act? What does this forecast tell me? On the other hand, many of us are using large language models lately. And another question that has to do with forecasting broadly construed is, to what extent can we trust an AI that says that it's 90% sure of the output that it has given? So, and these forecasts may look like, cute examples, smart, cute examples, but in reality, come to think of it, we as humans, we are using ML models to make forecasts and predictions for a lot of decisions that are extremely consequential, like, for example, medical decisions. So we want to leverage forecasts to make good decisions when the true information is not available or is hidden to us. And of course, as decisions become more consequential, then good forecasts are invaluable. And this is where calibration comes into play. Calibration, the way that Eric, Kunhe, and Nika and I think about it, we think of it as having two sides of the same coin. On the one hand, calibration can help answer questions like what should a forecaster do when they want to have certain downstream guarantees. On the other hand, calibration can be a vehicle or a tool to help us quantify the type of knowledge that one needs about their environment in order to make good downstream decisions. Now, in a more formalistic language, this may be a difference between, a more normative versus a more epistemic view of calibration. So as a concept, calibration has a very long history of studying it. And I will not go down right now into like the whole like history of calibration and whatnot, but throughout the tutorial today, we will see results from a lot of seminal papers that are from the 70s and the 90s, and we're going to see the citations there. But we will also see a lot of very, very recent papers because there has been a lot of renewed interest from the CS and machine learning communities and the Econ CS community in particular. Now, there's one thing that I also want to stress here, which is that, Nika, myself, Kunhe, and Eric were just four people that have written some papers in this area, and we wanted to give a tutorial so that, other people can be exposed and, so that they can have a 2-hour package of getting the basics and like hit the ground running. But there are many, many other experts in this area from our community that we want to give a shout out for. And in reality, we also have a lot of their papers that we cite throughout this tutorial. Two things that we want to highlight right now as broad is an excellent working draft of notes about uncertainty quantification by Aaron Roth. Aaron Roth has also a bunch of class notes, lecture notes about how he taught this class as time went by. And I believe there are also YouTube videos that I highly recommend that folks watch if you're interested in delving deeper into this topic. And also, there's a workshop at EC, which is going to take place in person, the workshop on swap regret and strategic learning. Now, I understand that nothing in this title shouts calibration to you, But as it's going to be obvious very soon, swap regret and strategic learning are actually very related with calibration. And I think both Eric and Kunha are going to allude to this relationship. So I wanted to bring this to your attention that encourage you to, both look out for Aaron Roth's notes, but also attend this other workshop. And with that, I will switch over to Eric, who is going to start talking to us about part one. I will stop sharing here.
Awesome. Let me set up my screen sharing. Great. I hope everyone can see my slides. Awesome. Great. So for this section, I'm going to be basically giving like a sort of like an introduction to calibration to make sure we're all sort of starting from the same starting point. And there's basically going to be three goals for the next like half an hour or so. The first goal is to sort of clarify what calibration means. So I'll give you the classic definition of calibration, but also like a more general way of thinking about calibration because I think the word has become pretty overloaded recently, and there's like a lot of you know different ways to define calibration. So hopefully give you like a better sense for how people like to think about it these days. The second thing is that we'll cover sort of why people that think about decision making like to also think about calibration. So what is this like sort of like fundamental connection between, for example, no regret learning and calibration? And then sort of the last thing that I'll cover is, there are a lot of variants of calibration that you're going to see in recent research and that, we'll also cover in this tutorial. And, hopefully we'll be able to like provide like a pretty good handle on like, okay, why are there so many variants and sort of like how can we think about them in like a coherent way? Great. And so, sort of like the high level, though, if you need something in the back of your head, it's that really calibration has become more of a language. And it's a language for describing how much information you need to know about the world in order to act within it. Great. So let's jump into the first part, which is sort of like covering the definition of calibration. I I think this is going to deviate a bit from the typical way in which calibration is defined, but let's just start off by considering a supervised learning problem. So binary classification, and what I have on the left is the true labels. So, uh, the bottom left corner is going to be red points, the top right corner is going to be blue points. And the plot on the right, let's just say these are the predictions that my model makes. And my model doesn't make binary predictions, it makes probabilistic predictions. So it tells me the probability that, something will be blue. And sort of these lines that I've drawn correspond to the level sets of my predictors. And this is what gives us sort of our classic definition of calibration, which is my machine learning model, my predictor, is calibrated if it is unbiased, in that, if I look at the average prediction, it matches the average label. And I'm not only asking that it's like unbiased over the entire data distribution, I'm asking that it's unbiased even if we zoom in on specific level sets of my predictor. So to make this a little more concrete, this like y minus px, that is the bias, and px equals v, that is like zooming in on a level set to v of my predictor. So for example, v can be like, okay, the prediction is like 0. Is that there's like a 70% chance of it being blue. And calibration would ask that, okay, if I zoom in on that part, if I look at the true labels, about 70% should be blue. That's not the case here, so we would not say that this predictor is calibrated. Yeah, so this like sort of like conditional unbiasedness was definition of calibration is sort of like classically defined where the events that we condition on are the level sets of our predictor. But sort of where things have moved with calibration is we're increasingly thinking of calibration as like this more general definition, where rather than just conditioning on, say, the level sets of my predictor, I might ask for like a more general class of events, right? For example, I could ask that I am unbiased conditioned on, a certain part of my domain or a certain part of, or like some like more complex function of my predictor. Really, the only restraint here is that we generally think of these events that we want conditional unbiasedness on to be independent of the true label. And that's just more of like a pragmatic thing where if like the events that we condition on are dependent on the label, then there may not even exist a calibrated predictor. And then the yeah, and then the last thing I'll say is just when we take this more general perspective of calibration, the sort of strictness of calibration, like how constrained the guarantee of calibration is, really is described by this like set like epsilon, right? This capital epsilon, the set of events that we want to be unbiased on. And one great example is if I ask my model to be unbiased, even if I zoom in on every individual point in my domain, then that is equivalent to asking that my predictor is the Bayes optimal classifier. In other words, if I want to have such a strong notion of calibration, I basically need to know exactly what the probability of y given x is for my entire data distribution. And so calibration from this perspective is just like interpolating between a more general notion of marginal unbiasedness to what you can view on the other end of the spectrum as Bayes optimality. One quick aside that I will make is that, I define calibration here for the supervised learning setting. And I think if you think about like, deep learning ML people in practice, that is the definition they'll go with. But calibration can also be defined for like online decision making. And what I mean by that is instead of, you have a fixed predictor and you're trying to describe calibration as a property of the predictor, maybe you exist in an environment and over multiple time steps, you are making forecasts. So you don't have a fixed predictor, rather you're making a sequence of predictions. In that context, you can still define calibration. And calibration there is if I just look at my empirical distribution of forecasts and I condition on different events in my transcript, am I still unbiased? This is like a very powerful notion, as you'll see a bit more in the second half, because this is a notion of calibration that makes sense even if the data coming in is not identical and independently distributed. For example, if I'm trying to forecast the weather and I don't have access to like a lot of features, then the data would appear like very would appear very like non-IID, and so you would need this type of like online calibration perspective. So then just the sort of recap, the textbook definition is just if I condition on level sets on my predictor is unbiased. The more general definition is, we're using conditional unbiasedness to measure how accurate my predictor's beliefs of the world are. And that's really the definition of calibration that we'll work with today. And then the sort of natural question you might ask is, okay, that definition of calibration makes sense, but sort of why does calibration and decision making show up in the same sentence? Like, well, what is the link here? Um, and I think a good way to think about this is that, you know, defining calibration is itself like still a very active area of research. And the way this like flavor of research looks is, okay, let's say that I want my predictor to be able to do X. For example, I want to be able to rely on my predictor to inform my picnic plans, or I want my predictor to be accurate enough that if I'm in like a mechanism design situation, I can convince agents to like follow it like faithfully. And if I have this type of goal in mind, then sort of the sort of research question I can ask is, what is a notion of calibration that is sufficient for this? Like, for what choice of epsilon does being unbiased condition on events in this epsilon give me this guarantee X? Um, and sort of like, a fun way to think about this is imagine like you are in Plato's cave and you can't see the real world. And these like predictors or forecasts, they're your mental model for the world. The question here is just sort of how accurate does that image of the world need to be in order for me to trust it as a surrogate for the real world, even though I can't actually look outside. And that matters because oftentimes I want to be able to make decisions, but I don't have a lot of information about the world. And so I want to know whether I can trust my predictors, my forecasters, to basically give me surrogate information to help make decisions. Um, and sort of like this is sort of like the premier modern application of calibration, which is it tells us how accurate beliefs need to be or predictions need to be in order to be relied on. And by reliable, what I really mean is if we act to maximize our utility, um, by assuming that whatever the predictor tells us is true, we really won't like suffer a lot of regret from making those types of decisions. So, like a very concrete example is, I don't know whether it's going to rain or not, but I can look at the weather forecast and I can treat the weather forecast as like an actually accurate description of, the dice that the world is going to roll when it determines whether it's going to rain. And so if the weather forecast is accurate, then I should be able to just trust it as a accurate reflection of the future and use that to decide whether to bring an umbrella. And just like make this now a little more formal mathematically, we can think of it in terms of, okay, I have a set of actions, and I have a utility function. And this utility function is both going to be a function of my action and, the state of the world. I'm going to define the state of the world to be binary here. So let's say it rains or it doesn't rain. Um, and my predictor is just going to tell me, okay, I have some access to features and I want to produce the probability that it will rain. This is like sort of just making it concrete. The A here is take umbrella, no umbrella. Utility will be my happiness if I take an umbrella and it does rain, or vice versa. And sort of the next two things we want to formalize is the idea that I'm going to act according to the forecast. And we do this by just defining my action as, um, you know, choosing the action that will maximize my utility. So this px times ua1, that is the probability that my forecast, this is the probability that my forecast claims it will rain. And my utility if I take the umbrella and it does rain, or I take an action and it does rain. And then the second one is just, the probability that my forecast claims it won't rain and my utility if it indeed doesn't rain. So this is sort of just like a surrogate for my expected utility. And if I act to maximize my, surrogate expected utility, then I can ask sort of would I have been happier if, in hindsight, I just completely changed what I did. So maybe whenever I chose to bring an umbrella, I actually just would actually just leave it at home, or, vice versa. And the natural way to formalize this is the notion of swap regret, which says that if I try to map actions that I took to different actions. So maybe I mapped the action of taking umbrella to not taking an umbrella. Then my utility, I can measure how much my utility would have increased. Um, I'll give you a little bit of time to stare at this, but this like difference within the expectation is the sort of gain in utility that I would have realized if in hindsight I wanted to swap my actions around. And so this is like sort of how we're going to formalize this notion of a predictor being good enough for decision making, which is if for any possible downstream agent, if for any utility that I have, I can rely on the predictor to make decisions and not incur a lot of swap regret. So if we go back to sort of like our original question, which is like what is good enough for decision making, then this notion of reliability is saying if I sort of trust my predictor, my swap regret, which I just wrote again there, should be relatively low. And this is like where we're going to start to come back to the calibration world, because there's a very classic theorem that tells us that calibration is sufficient. It is a sufficient property of a predictor so that we can rely on the predictor to make decisions. And in particular, if the predictor P is calibrated, then for every possible, no matter what your utility is, if you act according to the predictor, your swap regret will be 0. The proof here is actually pretty natural. One way to think about it is, you know, suppose whenever I brought an umbrella, I brought it because the forecast told me it would rain with an over 50% chance. Um, and because the predictor is calibrated, well, of the times the forecast was more than 50%, it would have needed to rain more than 50% of the time. And so if you are giving me an option to say, okay, if every time I took an umbrella, I could have swapped that action to not taking an umbrella, I obviously would not want to do so because, even though there might be a little bit of noise in the forecast, if I sort of look at all of the times I did choose to bring an umbrella, sort of marginally, that was a pretty good decision to make. And the formal proof follows basically the exact same way, and it ends up being pretty succinct. And I'll write it out here mathematically for you. I won't like read through it in too much detail, but the idea is I'm going to fix a level set V. That is basically I'm going to condition on a particular forecast. And I know that because my actions are determined by the forecasts, if I condition on um, my forecasts and the forecasts are unbiased, then if I condition on my actions, then the forecast should also be unbiased. And if conditioning on my actions, the forecasts are unbiased, then I shouldn't really gain much by trying to swap my actions around. And that's really the core of this like very classical theorem. Um, yeah, so I'll just give like a few seconds to stare at this a little more. One thing I will briefly mention is that this sort of like notion of sufficiency also goes the other direction in the sense that if I have a predictor where for every utility the swap regret is zero, that also actually implies that the predictor is calibrated. So, it's a very like a tight relationship between calibration and decision making.
So,
One
a
more thing
couple
I'll say
questions.
here. Yeah.
Why is any potential outcome here? So there's this variable y, but I don't. So you're not maximizing over y. This means for every y, this should hold.
The x and the y are being sampled over by the expectation. So we'll still just be in a supervised learning setting here to make things simple.
Mm-hmm.
And so the x and y are not being maximized. They're sampled from some like data distribution.
But you're taking expectation over x and y, and also like, sorry, maybe I'm missing something. But if my information is good, and if I swap my action, I should lose a lot, right? So I would expect this to be something very negative for my information to be good. No? Am I missing
Um,
something here?
if my sorry, so you're saying that if your information is good, then swap regret should be negative? I
Right. So
guess
if I
in this
act on, yeah, go ahead.
Yeah, I guess this maximum, this sigma, can also be it can be like a trivial thing, which is I'm not going to change my actions at all. And so sort of like this like max sigma expectation term will always actually be lower bounded by zero. Just because like that is measuring my incentive to deviate. And so my
I see,
incentive
I
to
see, I see. So you're,
deviate can always just be like I
mhm,
choose not to deviate.
I see. And this can also be generalized if I have non-binary action, or no, this is just for binary action.
So here, the actual like action space doesn't matter. So this is true like no matter how complex my action space is. I just wrote it for binary because calibration is a little easier to think about because prediction probabilities are a real value. Yeah.
Nice. And one last question, utility can be anything, the
Uh,
utility function?
Yeah, utility function can be everything. Sorry, can be anything. One thing I will say is that when we're starting to talk about like approximate calibration and like bounded swap regret rather than zero, it's like, like epsilon, then you have to like limit the scale of u. Like, okay, u can has like the range has to be bounded in 0, 1, but like the way it's written here, there's really no constraints on how we're defining the utility. One way to think about this is like this predictor is really extracting enough information about the world that like, it doesn't sort of matter downstream what your utility is. Like we still have enough information to like help you make your decisions.
Great, thanks.
Yeah. Right. So in terms of interpreting these decision theoretic guarantees, I do just want to briefly point out that there are sort of two ways to think about this that I actually might have actually informally jumped between. The first is, I can think of these decision theoretic guarantees as a question of if I am a forecaster, what is the sort of performance guarantee I should strive for if I want others to trust me? Right? Like if I am a weather forecaster or I'm Nate Silver, what claims should I like strive to make about myself so that like people will follow my forecasts? There's also like a more egocentric perspective. I think this is the perspective that I like spoke in the language of for this part, which is how much do I need to know about the world in order to make decisions? Um, these will be you can pick whatever perspective you'd like depending on the application you're interested in, but really the only upshot, the only like high level thing that's important here is that like, calibration is a way to formalize decision theoretic guarantees, however you want to actually use these guarantees. And one last thing I'll mention is that, there's been a lot of like really interesting work on, what like other sort of downstream guarantees that calibration gives are. I can't like hope to cover all of them and flashing them wouldn't like give that much utility. So I'm just gonna cover, I think, two of like the most two of like very seminal ones in the field recently. One of them is omni prediction. So this isn't even anything necessarily to do with decision making specifically, but rather it's saying that, typically in supervised learning, we think that I have a data distribution and I have a loss function, and I want to produce a prediction that minimizes that loss in expectation. Omni prediction is saying that I don't just have a single loss, I have an entire family of loss functions. And it can be like an infinitely large class, like the class of all like Lipschitz loss functions. And I not only want to learn a model that is like good for a single loss function, I want to learn a sort of predictor that is so accurate that no matter what loss function you give me, I can find some data independent processing of that predictor that is actually optimal for that individual loss. Um, and so this is like a very powerful notion. It seems like it's asking for something that's like a lot harder than normal learning. But what you can actually show is that because this is a consequence of calibration for an appropriate set of events, um, for an appropriate set of events, that the actual like the worst case sample complexity of omni prediction is not like that much asymptotically worse than ordinary pack learning. And sort of in a similar vein, there's a notion of multi-group learning. Um, So normally in pack learning, what we ask is that, okay, you perform at least as well as the best predictor for the data distribution. But we can ask for a slightly more challenging performance objective, which is I'm not only going to ask to be optimal on my entire data distribution, even if I zoom in on different subsets of my domain, I'm going to call those groups. My prediction is still going to be individually optimal. Sorry, those expectations should be conditioned on X belonging in G. Um, and so this is like asking for something stronger than pack learning, right? I'm asking that I not only beat the hypothesis class overall, but if there's some group for which hypothesis 1 is the best, some region for which hypothesis 2 is the best, then I have to basically perform better than H1 on group 1 and better than H2 on group 2. And this is also something that follows nicely from calibration. And because of that, is something that you can show is not that much more expensive in the worst case than ordinary pack learning. And these are all sort of the same like downstream decision making flavor, where you want to give guarantees and you don't really know what your downstream application is, whether that's not knowing what the downstream utility function of agents are, or not knowing what your loss is, or not knowing like what subset of the domain you're interested in. This is where calibration starts to become like a really powerful language. Yeah, so just briefly recapping, calibration, it describes how accurate your beliefs need to be. Originally, we looked at it just for like level sets, and that was really powerful because it turns out to be like sort of equivalent to allowing for downstream no regret decision making. but there's like a lot of more recent extensions that give us a whole bunch of, an entire zoo of like really cool guarantees. Great. So I guess the sort of like last part that I'll cover, the last section I'll cover in this part is, getting a sense for all of these like different notions of calibration that arise and sort of how we can try to think about these different notions of calibration in a pretty unified way. So I'll just start off by, just briefly like talking mathematically through some common measures of calibration. So one thing I'll say here is we're no longer talking about what perfect calibration looks like, where we're trying to measure what calibration error is. And so the sort of like classic definition here is, I'm going to condition on a level set and measure what my bias is. Uh, for those of you that are familiar with calibration, I'm working with an L infinity norm over the level sets here. Classically, you work with like an L2 norm. I'm going to fix L infinity because it just makes everything a lot easier. Um, and I think sort of like a calibration measure that actually brought a lot of attention back to calibration was multi-calibration. This is like, it looks very similar to normal calibration. The only thing is, not only am I asking for my model to be unbiased, conditioned on level sets of my predictor, I'm asking it to be unbiased, conditioned on level sets of my predictors and my features belonging to certain subsets of the domain. One way to think of this is I'm not only asking to be calibrated marginally, I need to be calibrated in each of several subgroups of the domain. And these like subsets of the domain can be like intersecting or like really weirdly shaped. One more sort of calibration measure that is like pretty qualitatively different from the other two, and I think is like sort of like quite interesting, is instead of looking at a level set, conditioning on a level set of my predictor, I'm gonna condition on the epigraph of my predictor. So whenever my prediction is less than a certain amount, I'm going to ask for unbiasedness. Um, this is actually like a very powerful notion. For example, it gives you like optimal rates for like omni prediction. It has nice truthfulness properties. It's testable. Um, that like I worked on this with Mingda, and like there were two other groups that like reached the same definition concurrently, but like with completely different motivations. I think some other definitions of calibration that are, I think, especially important for decision making is U calibration. So U calibration is basically a notion of calibration for like minimizing downstream external regret. Calibration decision loss is like sort of like an improvement for downstream swap regret. Uh, there's like also some more that I won't like formally define. There's like smooth calibration, which is instead of like conditioning on indicators of my level set, I condition on like smooth functions that, instead of being like a delta function, it's like sort of like a tent looking function. There's also distance to calibration, which is sort of like measuring the L1 distance of my predictor from the closest perfectly calibrated predictor. I guess the point here is I'm sure I'm missing a lot more, but there's a lot of calibration measures, and they exist for a very good reason, which is that like different applications call for different things. And usually we want the minimally sufficient notion of calibration because we want to obtain that downstream application as efficiently as possible. So you'll often see papers that sort of take this framing where, okay, calibration measure one, it's sufficient for X, just like calibration measure two, but it's a lot weaker than calibration measure two and it's efficiently attainable. So it's like a nice thing to study and a nice thing to understand. Um, like I think a very good example of this is like, okay, multi-calibration suffices for multi-group learning and omni-prediction, but it's like polynomially more expensive to obtain in the worst case than step calibration. And so step calibration is nice because it's sort of like, it suffices as well for these downstream applications. Yeah. So a lot of calibration measures, the sort of like menagerie of calibration measures exists for like a pretty good reason. And sort of the next thing to deal with here is, okay, if there's so many definitions, if you really want to understand a space, you need like a more general way of like thinking about all of these notions of calibration. I think the personal way that I like thinking about these notions of calibration is sort of like from like a more classical geometric perspective. For those of you that are familiar with Blackwell approachability, this will look familiar. If you aren't, it's totally okay. That won't be necessary. But let's just consider, for example, multi-calibration. So this is a definition I introduced in the previous slide, where we're asking for unbiasedness conditioned on both the level set of my predictor and looking at specific subsets of the domain. The sort of nice thing is that you can always write these calibration objectives as finding a min-max equilibrium. Where the min-max we're trying to find is we're trying to find a predictor that minimizes the calibration loss. And I can actually rewrite this like multi-calibration loss in terms of like three variables. The first variable is G. This tells me like what is the subset of the domain I'm interested in. The second variable is V. This tells me, okay, what is the level set I'm interested in? And sigma here is just replacing the role of the absolute value. It's telling me whether I'm like over or underestimating. And so being calibrated really just corresponds to simultaneously minimizing a bunch of these losses that they actually look almost linear, right? Um, each of these like sigma times y minus px times these indicators, they end up being like very like easy or natural losses to try to minimize. And what we're going to see in a bit is that that's what contributes to calibration being so efficiently attainable. And so if we're to take a game perspective, let's sort of imagine there's actually two people here. The first person is the learner, and their job is to produce a predictor. And let's say they actually produce a sequence of predictors. So we're going to consider like a multi-round game. And also have an adversary, and their job is to sort of like pick out where the predictor is biased and it shouldn't be biased. So it'll produce critiques, and each critique will basically be a bundling of a group, a level set, and a sign that tells us whether the bias is due to over or underestimation. And if we're to write this as a game, then the sort of payoff function here is just this like expected like conditional conditional measure of bias. And so one way to interpret this is, okay, my learner's job is to constantly propose new weather forecasting models. And my adversary's job is to basically point out, okay, on the days where you forecasted like a 50% chance of rain, you've tended to overestimate the chance of rain in the state of California. So, that's a place where you're sort of violating this multi-calibration guarantee by like quite a bit. One thing I will briefly say is this was written for multi-calibration just to make it more concrete. But if you want to think about this for the more general notion of calibration, it'll take this form where instead of critiques being like sigma, v, and g, it'll be like sigma, which is replacing an absolute value, and w, which is like some like arbitrary weight function of pt and x. And that's sort of going to capture the conditioning on like a pretty generic event that can depend arbitrarily on pt and x. All right, so back to the game perspective. We'll go back to multi-calibration because it's easier to think about. And so we have a learner. Their job is to propose a predictor they think is good. You have an adversary. Their job is to propose like, okay, this is a part where you're biased. This is the direction you're biased. This is me trying to be a very critical auditor. And so the next thing we can ask is, what do calibration algorithms look like? And what I'm going to claim is that every sort of calibration algorithm that you can imagine will be within like the following recipe book. So we have this game as before, and sort of like the degrees of freedom will be okay, I can sort of have my learner propose new predictors, and then my adversary will react to the predictor by saying, okay, this is where you're sort of doing badly. And then my learner will propose a new one. So this is like one option for a game dynamic where my learner has to move first. I can also do the opposite thing, which is I have my adversary propose, okay, historically you've been like under or overestimating in this region. And so the learner has to look at the critique and basically update its predictor. So in this sort of game dynamic, the adversary is moving first. And sort of which one you choose to move first is going to depend on sort of what your goal is with your multi-calibration algorithm. If you're in a batch setting, so like a classical supervised learning setting with the data distribution, and your goal is to produce a single predictor that is calibrated, you'll want to typically work with a game dynamic where the learner moves first. If you're in an online setting, let's say you're trying to sequentially predict in an adversarial environment and you want your predictions to be calibrated, then you'll use the second game dynamic where the adversary moves first and the learner reacts. Um, so that's the first sort of degree of freedom when you're designing calibration algorithm, which is they'll all end up taking this form, but you can choose who moves first, who reacts. And the
And
second degree of freedom is picking out, yeah.
is it clear why when it's a batch you want the learner to move first, and when it's an adversary, and when it's online you want the adversary to move first? Is it obvious, or am I missing something?
It is not obvious. I will cover that in the next slide.
Okay, okay. Thank you.
But yeah, it'll have something to do with actually the convergence of Stackelberg equilibria. So it's like a very short and cute thing. Um, but so that's the first degree of freedom, which is who moves first. The second degree of freedom is sort of like how are we like what algorithm is the learner or the adversary running, right? Like because I haven't actually defined how they're choosing to propose or react. Um, and sort of the claim here is that any calibration algorithm you give me for like all of these different variants of calibration, you can always cleanly write them in this fashion where, they either have one person move first, the other person move first, and they're really just using like different choices of algorithms. And they also tend to actually coincide with like pretty like classical online learning algorithms, which is like a very cute thing if you're familiar with those tools. Okay, so this is sort of our recipe book, right? There's the order of play of the game dynamic because we've set this up as solving a game. There's the choice of the learner's algorithm and the choice of the adversary's algorithm. And just to like bring it back to the weather example, to make this concrete, you can think of it as okay, how does the learner develop new weather models? How does the adversary audit the models? And does the adversary raise concerns preemptively, or do they just react to the newest model that the learner put out? Um, as long as you can sort of like concretely answer these questions, you have for yourself a calibration algorithm. Um, so why do game dynamics work? I'm going to focus on the first dynamic where the learner moves first. This is the dynamic that works for the batch setting. Um, and the reason that this works is the following, which is if the adversary always best responds, and the learner has to move first, but the learner can still be no regret. If both these conditions are fulfilled, what I know is that after long enough, at least one of the learner's predictors must be calibrated. Um, for those of you that are familiar with using game dynamics to find Stackelberg equilibrium, what you'll notice here is we are finding a Stackelberg. This is a pretty classical Stackelberg algorithm where the learner is the principal. Um, the other game dynamic is for the online setting, and this is where the adversary moves first. And in this setting, we actually walk away with a different guarantee. Instead of the guarantee that at least one of the predictors is calibrated, what we have is that on average, the predictors are calibrated over all time steps. And so to, I guess, answer your question before, which is why can't I use this second game dynamic for the batch setting? You can by using an online to batch reduction. But the weird thing is you'll end up with like this randomized predictor that is technically calibrated, but it's not going to be calibrated in the natural sense. And it'll be a little bit hard for me to mathematically define, but just like the intuition here is that the definition of calibration is not a convex one. And so online to batch reductions will inevitably hit that barrier. And so, this sort of like second class of algorithms, second class of game dynamics, they'll really only like let you do to be calibrated in the online sense. Um, which if you're fine with like this like weird like convex variant of calibration, you can still use for the batch setting, but I don't think that's what people normally think about. And sort of just to give more intuition on the first dynamic, because that's what I'm going to dive into with an example now. Um, One way to think about this, why is at least one of the predictors calibrated, is that if the learner has a good procedure for producing predictors, like it's no regret, and the adversary is constantly pointing out the biggest problems, then eventually the learner will make a good model. Just like after long enough. Yes, Amy.
Thanks. So super interesting. So for the min-max perspective, which I think you said we should think of it as a min-max game, are you saying that we have two different Stackelberg equilibria depending on who moves first? So that's why we get either the online or the batch situation? Is that somehow?
Yes. So I think if we want to
We
think
don't have
about
a minimax theorem is what I'm, sorry, so there's no minimax theorem here. Is that right?
yes, and the reason there's no minimax theorem here is like calibration is itself not like I guess it's weird. I will say that like if you're working with calibration in the online learning setting, calibration is like it's like a convex like objective, and so the min-max theorem does hold. So you can prove things using min-max. But when you're working in the batch setting, then calibration is no longer like it is no longer like a cleanly like convex thing, and so the min-max theorem as is doesn't hold. And so these two Stackelberg equilibria end up looking different, and that's why the game dynamics will sort of end up with different guarantees.
So somehow the game has changed. So I'm a little confused about where the game changed. Like we have, right, two players and one objective function. So I don't understand how whether it's batch or online changes the game so that we do or don't have the min-max theorem.
Yeah, I guess this is like
sense?
yeah, this is a little bit like a bit of a subtle point that I brushed over, but when we're in a batch setting, the way we define calibration is that it's a function of your predictor. Whereas when we're talking about calibration in the online setting, it's a function of your predictions. And I think like that like mathematical distinction is like I guess like a bit hobby is like a bit difficult to just like verbally
So there are two different objectives, you're saying. Like the definition of a calibration changed in the two games. So
yes, it
that's why
changed
the
in
two different equilibria when I have two different games. Even though I switched the order of the players, I also changed the objective.
Yes. Yeah.
Okay, that makes sense.
You can go from like online calibration to like a batch calibration definition, but again, it'll look a bit unnatural. Just because of a lack of linearity. But
Thank you.
so yeah, just to briefly recap the two dynamics. So the first one is the text box on first. I choose PT first. The auditor moves second. That's the one that we'll go with. The bottom one is the other dynamic, which is more for online learning. So I'll just like briefly skim through like how you actually obtain calibration. This is multi-calibration, and the recipe we'll use is the learner will move first because we're going to work in a batch setting. We're going to pick the predictor using a multiplicative weights algorithm, and we're going to have the adversary respond by sort of best responding with an adaptive data analysis algorithm. I won't go through this proof formally, but the actual claim, the actual theorem that you get is that this will only cost you 1 over epsilon cubed data points. And the reason for this is, I'm going to make two claims. The first claim is that in order to choose these predictors, I don't actually need to use samples, which might be a bit surprising, and I'll justify that in a second. But I do need about square root t iterations. Like my regret will be square root t. So if I want like epsilon regret, I need to set like big T to be at least 1 over epsilon squared. The second claim is that my adversary, they don't sort of need T to be large, but they will need a lot of samples in order to best respond. And if you plug in T here as 1 over epsilon squared, what you'll end up with is that 1 over epsilon cubed sample complexity. And again, I won't cover the proof formally, but the reason why you can have this magic where the learner doesn't actually need to see data points is that I can actually run this algorithm where for every different point in my domain, I have a no regret algorithm learn what my prediction should be. And let's say that my adversary has fixed a choice of level set and a subset of the domain. if I know that if I am a point in the domain and I know that I fall within the sort of region that the adversary is auditing, and the adversary claims that, we are underestimating the label, then I'll know to slightly increase my label. And so because of this, I can just sort of like react to what the adversary is claiming in order to sort of update my own prediction. I don't actually have to see the data distribution. And you can think of this as like playing Marco Polo, right? Like my eyes are covered, but I have an auditor that is sort of giving me signals about whether I'm over or underestimating. And that really is the magic for why calibration can be so efficiently obtained, which is that we have these almost linear losses where these types of tricks do work. One last thing I'll say is that this sort of like example of a proof of the multi-calibration algorithm I gave, because we can write like every calibration algorithm in this in this framework, the proof for like complexity also follows like pretty generically, which is I make 3 claims. I need X samples for my learner, I need X samples for my adversary, and I need Y iterations to converge. And if all of that follows, then the total number of data points I need is just like on the order of X times Y, which is a simple enough recipe to follow if like you find yourself working with your own definition of calibration. So yeah, if we go back through all of these definitions of calibration that we talked about, these all follow from the same algorithmic framework. So if you have your own application in mind, you really shouldn't be too afraid to just ask yourself, can I write this as calibration? And if I can write this as calibration, like how can I sort of decompose the problem into like these like typical recipes for calibration algorithms? There are still a few unknowns here. Like I said, it's still a very defining calibration is still a very active area of research. So, there's we still don't exactly know, like for a lot of like applications, what the sort of minimally attainable minimally like and most efficiently attainable notion of calibration is. We also like are still just learning like which notions of calibration are actually equivalent to each other. For example, the relationship between like smooth calibration and distance to calibration. I think something else that is like a very interesting flavor of research in this area is just like identifying new downstream applications that are interesting. I think omni prediction is a great example of that like flavor of research that has been like super impactful. And then, yeah, I guess the sort of last thing that I'll mention is that when we talk about calibration, there's also like a whole zoo of like interesting things that happen when, calibration itself starts to become an objective. For example, what are the incentives that it creates for forecasters? What are the, what are like the broader like ecosystem consequences of like using calibration to measure to measure like the accuracy of people's beliefs. Um, and yeah, so that'll conclude the part. Sorry for running a bit over time. If you were to walk away with 3 things, calibration means conditional unbiasedness. That's like a more generic, like modern definition. It defines sufficient conditions for forecasts to be reliable enough for you to make decisions based on them. And sort of the last thing is it might be a little bit intimidating, like the calibration literature, because there's like so many different like papers and definitions, but they're really all just like following the same flavor of trying to like quantify how much we need to know about the world and reasoning about like their algorithms and complexity. We have like pretty good general recipes and frameworks for doing that within.